Hello, everybody. This is Eyal. I'm in Florida. The time here is 1 p.m. And welcome to our December meeting of the virtual user group of Enterprise AI. Today we have Johan Vos. I hope I'm pronouncing the name correctly.
Yeah, you did.
And let's just move to Johan and start with him, and then we can talk a little bit more afterwards.
Thank you. So I hope that my screen is being shared and that you see it. I think so. So we will talk about federated deep learning with Java on the client and Java in the cloud. So I'm Johan Vos, and I'm one of the co-founders of Gluon. Gluon is a company that enables the Java mobile enterprise. And to very briefly show why that is important, if you look at the cloud landscape, then you see that many things in the Java cloud world are very much known and under control. Cloud native development is very common in Java. You have microservices as an architecture, CI/CD, containers, DevOps. For beyond the cloud, where edge systems and devices like mobile, tablets, laptops, and so are living, the situation is less clear. And what we try to do is to make Java first-class citizen there. And with the Java FX11 user interface, it is very convenient to create Java applications that run on all those edge devices, mobile, laptops, and so, and connect them to cloud devices. And as we will show in this presentation, this is very relevant for deep learning, and it can really lead to some benefits. So what will we discuss today? First of all, I will quickly go over deep learning, give some examples, talk about forward propagation to do predictions and backward propagation to do training. We'll talk about training on a server. Then we'll do predictions on a server. We will move to doing predictions on a client. Then we will talk about training on a client. And finally, the end goal of this presentation is doing training on a federated system. So before we go into the details, let me quickly talk about the problem. What we know from deep learning and machine learning in general is that it can be very accurate and can be very helpful if you have at least enough high quality and labeled data. So that's a requirement. On the other hand, the data has to come from reliable sources. And in most cases, data is obtained via consumer devices, and it's not very easy or legal or a good thing to send all the data from end user devices like mobile phones and so to cloud systems. There are privacy restrictions. You cannot just take a user's media and send it to a cloud system and use it for whatever purposes. And legal restrictions like GDPR prevent you from using users' data without their knowledge. So there are some restrictions here that if you're not able to tackle them, that will prevent the success of deep learning. So what is the solution that we propose here? Well, with Java and DL4J on the mobile and embedded clients or on laptops and so, you can enhance the neural network model. So in this case, the data can stay on the client, so you do not violate the user's privacy, and the neural network on the server still becomes better. And the neural network can benefit from updates on the client without the data being sent from the client to the server. And when many clients do this and cooperate this leads to federated learning. So let me briefly talk about deep learning. This is not a course in deep learning. At the contrary, we do recommend that if you want to know more about deep learning, that you go to one of the resources online. For example, the resource at the bottom of this slide brings you to DL4J, and it goes to their page where they explain deep learning for beginners. But very briefly, deep learning is a class of machine learning algorithms, and it can be supervised and unsupervised. And typically, raw input data, it can be media, for example, images or video or text or numbers, traverses a number of layers. And the last layer is typically the result, which is, for example, a classification. So an example of this is we have an image that shows a bike. And this image, of course, contains pixels. And we can put a number to each of those pixels. Or we can put 3 numbers, for example, that are the red, green, and blue value. We can send those numbers through a neural network, and the result will be, well, a classification. For example, this is a bike. In practice, it's more likely that the network will say, there's 96% chance that there's a bike in this picture, and maybe 1% chance that there's a car in this picture. But for simplicity, we assume that the neural network will make a prediction and classify the input data. How is this going under the hood? And this is a picture that I borrowed from the DL4J site. In deep learning, you have a number of layers. You have an input layer, an output layer, and one or more hidden layers. And the data traverses from the input layer to the output layer via the hidden layers. And in those layers are a number of nodes. And the value that is assigned to a node is calculated based on the values of the previous layer, some weight coefficient, and some bias coefficients. And then some linear algebra is used to traverse from the input layer to the output layer. And what you want in the end is that the result in the output layer is something meaningful. For example, that the output layer, where you have different nodes, and one node might be, for example, the probability that there's a bike in the picture, that output layer becomes 1, and all the other node becomes 1, and all the other nodes become 0, based on your inputs. With deep learning, you can do training, and this is one of the key elements in deep learning. If you provide data that is labeled, then the deep learning algorithms can become better, because if they make wrong prediction and then they know that the prediction was wrong, they can optimize the neural network and they can become better and better. So with after a number of iterations, the accuracy of the network will become better. So it's sort of self-learning. It will adjust its coefficients so that the likelihood that it can deal with the training data increases. And in numbers, this means that the weight coefficients of the network are adjusted, and that in order to decrease the error. So the predictions should become much better by iterating a number of times over the input, and with each iteration, the result should become better. So if you want to learn more, you're really encouraged to go, for example, to the DL4J website. So that's all that we will explain about deep learning itself for now. What is relevant for developers, like Java developers, for example, is that that you know what are the requirements for deep learning. What is needed on a laptop, on a mobile device, on a cloud server, or whatever, to do deep learning? Well, basically, it mainly comes down to high-performance linear algebra. If you want to make predictions, so you send some image data and you want to get some output results, then some computations have to be performed. Mathematical linear algebra is needed. Predictions are still relatively easy. You don't need too much resources, but the training is more complex. Complex in a way that it requires more resources. And I'm not even talking about data scientists who have to adjust the algorithms and making sure that the initial parameters and the activation functions and the number of hidden layers and so is optimal. That is a different problems, and that is something that data scientists are very good at. In this presentation, we're not talking about those issues. We're talking about computational issues associated with deep learning. The other requirement for deep learning to generate good results is that you need high-quality data and preferably labeled data. And the more high-quality data and the more labeled data, the better. So briefly about deep learning for J. The reason that we talk about deep learning for J is that this is one of the my favorite deep learning frameworks in Java, and as you will see, it's very applicable to Java on the client and on the server. I'd like to start with a quote. When science shops become mature, they turn into Java shops. And I actually borrowed this from a quote from James Governor from Redmonk, where he said, when web shops become mature, they turn into Java shops. What we mean with this is that in many cases, data scientists start not with Java, but with, for example, Python or some more data science specific language. And for very good reasons, because those languages are created specific very suitable for data science, deep learning, machine learning in general. You can easily prototype things, adjust some parameters, check the results, tune some configuration, and so that is what is very often used in order to create a prototype and to test the validity of some model. And then when the prototype is working, the model, the network is trained, and it's all looking good, you want to put your project in production, and then you will face very different issues, like, for example, security, multi-threading, garbage collection, integration with enterprise functionality, with database integration, storage requirements, and so. And that is where Java is very good at. Now, if we can bring Java into the picture earlier, it becomes much easier to make the transformation between proof of concept projects and experiments towards production projects. And by bringing Java in much earlier, you reduce the risk that your project will fail between the stage of research and development and prototyping and the stage of production and the real mass rollout. And Deep Learning for J can help you with that. So you can go to deeplearningforj.org to find more about it. It's basically a Java framework that provides deep learning functionality. And for its implementation, it uses a number of native mathematical libraries. And if available, it will use the GPU or the GPUs available on the systems that you want to run at. Deep Learning for J is created by SkyMind. It's open source, and you can find it, the code at GitHub. So basically, it's a high-performant linear algebra framework for Java. Now I have to say something about, I've been talking about deep learning in Java. Before we go on, there's one technical detail that I really should stress. Java runs not only on the enterprise in cloud systems, but it runs on mobile as well. In this session, we won't go into the details, but if you want to know more about how to run Java on mobile, you can go to docs.gluonhq.com/getting-started. And there you will learn how you can use your existing Java 8 applications or create new Java applications and run them on iOS and Android devices or on embedded devices. So at this moment, we have support for Java 8, and we're working on Java 11. This is not just a Java dialect, or this is not a subset of Java. This is really the Java as it is being developed in OpenJDK. So it's really the real Java that is running on mobile. And for the user interface, well, Java has, with JavaFX, a great UI platform that allows you to create cross-platform UI applications. And doing so, you can reuse 100% of your code. So you write an application once in Java on desktop, and you can reuse the code. And one of the great things about this is that the code that you use on the server in the cloud instances to do all those machine learning steps also works on mobile and embedded devices. And spoiler, it's not even, people might think that it would be much slower on mobile devices or on embedded devices because they typically have less resources. Well, that is not always the case, because on mobile devices, the GPU is typically performant because people use GPUs on mobile devices for UI rendering and so we can really benefit from this. I have to mention that, well, because we often get questions like, yeah, but you can't run Java on iOS. That is true, but you don't have to worry about it. The tools that we provide allow you to run Java on mobile devices, and under the hood they will use an AOT compiler that will compile and optimize your applications for the best performance on those devices. So for now, we won't talk about the technical details anymore, but just keep that in mind that your Java code runs on mobile as well. Now we're going to start with the first case, which is training our neural network on the server. If we want to train a neural network on a server, and remember, this is needed if we want to make predictions, we need a very well-trained neural network. What do we need as input? Labeled data. Now, there are many public available data sets that contain high-quality data. Of course, while this is very good to create proof of concepts and to test applications, in most projects, you need some project-specific training data. And this project-specific training data needs to be available on the server because that is where you want to do the training. Apart from the data, you also need code, of course. And in the code, the algorithms, you specify the topology of your neural network. You define how many layers and what layers that you use. You have to initialize your network, fit it with the training data so that it can learn and become better and better and better. And you also evaluate your network using test data. We won't show too much code, but I think, well, actually, this is a talk including Java in the title, so I should at least have one slide with Java code. This is how we define a neural network using DL4J. So this is just an example, but the general idea is general, of course. We create a neural net configuration builder where we define our neural network. We provided some information, like, for example, what is the optimization algorithm that we want to use. In many cases, the stochastic gradient descent approach is used. You give it some information about the updater, about the learning rate, and then we specify the number of the layers. So remember, from the very beginning, a deep learning network has a number of layers, 0 or more hidden layers, 1 or more hidden layers, sorry, and we have to define them. We have to define how many input nodes this layer has, how many output nodes, how the weight coefficients are initialized, and what activation function is used on this layer. Again, we're not going to explain what those concepts really mean. If you want to know more about the weight coefficients and the different activation functions, you can find it at the deeplearning4j.org website. Ultimately, based on the configuration, we are going to build the network, and then it can be used for training. If we want to do the training, we need, of course, the training data. There are many different ways on how you can supply training data to a deep learning network. In this example, we use a CSV file that contains labeled data. You can, well, there are many different ways for providing the data, but a very easy example is using the CSV file, where you have both the raw data as well as the label so the result that you would expect that the network will detect as well. The input data can be pre-processed and optimized for the neural network, and ultimately we call the fit method on the network that we created in the previous step, and the network will be trained. If we want to do predictions on the server, once the network is trained, we can use it to make predictions. And in a typical case, the client sends raw data to the server. And the server then will use the network that we just trained to make predictions and send the predicted result back to the client, for example, via a REST interface. So in this case, the client makes a picture, and the picture contains a bike. The client will then send the raw picture, so all the bytes that are in the picture, to the server, and the server will then maybe do some pre-processing and do some more processing, call the neural network, and the result of the what the network thinks that is in the picture will be sent back to the client. There's an additional benefit in this approach. Is, for example, when the network thinks that this is a car, and the user says, "No way, this was not a car, this was a bike." So if you have a smart user, the smart user can send this information back to the server, and the server can then use that information to make the network better. So it can use the training algorithms of the deep learning APIs and improve the neural network. And that is actually how neural networks often become better. In practice, of course, this might be, the example that I gave is not very usable because end users do not want to spend time by typing, this was not a car, this was a bike. It's done much more subtle. For example, what can be done in autonomous driving is that the steering wheel thinks that you want to drive to the left, but if you move the steering wheel to the right, by doing so, you give implicit input, and you implicitly tell the network that it was wrong, that it shouldn't have gone to the left, but to the right. But for simplicity, we assume here that the user explicitly gives input to the neural network and says, this was wrong. And in both cases, the result is that the network can learn from the user input and becomes better and better. There are some drawbacks, although, on this approach. For example, we're talking here about the client sending some raw input to the server. Now, setting up a client-server connection can take a long time, especially if you're using HTTP. Well, a long time might, for many web applications, this might be sufficient. HTTP might be sufficient, but given the example of autonomous driving, you don't want to call a network function to make a decision that you need to make in 5 milliseconds, for example. So in many real-world cases, clients need to get the data much faster. Also, your device, your client, might be offline. If you're using your phone for an application that requires deep learning, and you're not always connected, then you can't get results back from the server. And finally, and this is increasingly becoming more important, this approach requires you to send raw private data to the server. And if we're talking about images here, this can be a problem because you're not only sending your own image to the server, you might as well send images from your camera, which include other people, to the server. And you probably didn't ask those other people for permission, but their raw data is being sent to a server. Now you can trust the provider, the cloud vendor, that he is treating all the information with confidentiality. But even then, you're legally not allowed to just use whatever data that you can find and send it to whoever you trust. That's where GDPR and other legislation comes into place. So while this approach is really good, there are some issues that need to be solved. And one step in the right direction is that you can also do predictions on the client. And now remember what we said earlier, that Java runs on the client as well, not only on desktop and laptop, but also on embedded devices and mobile clients. And the same Java code that we run on the server can also run on the client. And that is very important because you do not have to learn a new language or write a new deep learning algorithm. You can leverage the code that you wrote on the server, and the same code that's being used to make predictions on the server can also be used to make predictions on the client. And that is what we show here in this example. We have somehow the neural network on the client, and we make a picture of the bike again. And instead of sending that picture over a network connection to the server, we just send it to the neural network in our own application. So our application is bundled with a neural network. Actually, a neural network is mainly defined by a bunch of numbers. Those numbers define the weight coefficients, the biases, and some more information. So that is just some numerical input that's available on the client. And the same API that we use on the server to query the neural network can be used on the client to query the neural network as well. So in this case, for example, we give those pixels as input to our API. It doesn't have to be a REST API, like in the case of the server. It can be a much faster API, and the network will reply, for example, this is a bike. So I really want to stress that the same prediction code that you use on the server can run on the client as well, if you use DL4J and Java on the client. Now, the model, as I said, is mainly a bunch of numerical values that can be serialized and sent from the server to the client. It can be contained in the application, or you can have a strategy where you synchronize the client every day or every month or so with the server. And because you initially trained the model on the server, you do not need to retrain the model on the client anymore. So the model on the client is already a good one because you trained it on the server. So what are the benefits? We do not need to serialize data from the client and send it to the server. And we get instant feedback on the client. We do not have to make a call to the server. If we lose connectivity, no problem. We do not require connection to a server. And we preserve the user privacy because we are not serializing data from the client to the server. Again, what is required in order for this approach to be successful? You need to be able to do computations on the client. And again, this can be done using Java on mobile and DL4J. On mobile, the DL4J implementations will use the hardware acceleration of the GPUs if available. So DL4J uses OpenBLAS or a BLAS implementation. And depending on which device and which GPU and configuration you have, the best matching native implementation will be used to do the computations. So it's really pretty performant. So what were the drawbacks that we had before? Well, what if the client needs the data faster? That's not an issue anymore because the client has the data faster. If the device is offline, no problem. We have everything we need locally. And we don't send raw private data to the server anymore. So that's fine. There's a new drawback, though. As we showed in the client-server example, the model can improve. You can train the model by telling the network when it was wrong. But in this case, we don't do that anymore. So that's a drawback. Don't worry, we can fix that, because you can do training on the client as well. And the feedback that the user gives on the client can still be used to improve the model, because not only the code for making predictions is the same on server as on the client, but the code for training the network on the server can also be used on the client. And again, this is possible using Java on mobile and DL4J. And so that means that we can retrain our neural network on the client by using the data and the actions of the user without sending this data back to a server or a cloud. We just use the local computation power to make the network better. And this is extremely important. So your network will learn from its mistakes if you provide input, and it will become better without you giving up your privacy, you as an end user. So how does that work? It's actually very similar to the to how it works on the server, except that the model is now kept on the client. So the neural network is being updated on the client. That's as we said in the beginning, making predictions on the client is relatively easy. It requires computational power, but not that much horsepower. If you want to retrain your neural network, that requires typically more power. That requires more computations, more iterations, and therefore that is something that you, in most cases, should not do synchronously. But there are enough approaches how to do that asynchronously. For example, you can schedule a job that runs at night on a mobile device, or when it's plugged into a power socket, and when the load is not high, or when the device is idle. And at those moments, you can retrain the neural network of your application on the client. So you can still do the same as that you would do on the server. But then you do it on the client, and all the data that is used to retrain the network stays on the client. So that looks like we solved the remaining issue, but there's a new issue now. We improve the model, but as you can see from this slide, we only improve the neural network on our particular client and not the network on the server. And that's a pity, because if the network on the server is used as starting network to all those clients, it would be great if it can improve as well, because then the new clients will automatically have a better network to start with. So the new drawback, so we fixed the previous one, the model improves, but we have a new issue. The server model is not becoming better. And that is something that we would like to solve, and that we can do in federated learning. If you have, imagine that you have multiple clients operating the same way as we just described. If those clients enhance their local copy of the neural network model via client-based training, then the model on the server can somehow average the model changes if they are submitted back by the client. And that's what we call federated learning. So as a result, the model on the server becomes better, but the data stays at the client. And it's important to make this subtle distinction. We still send, in this approach, we will send data to the server again, as you can see in this picture. But the data that we're sending now is not the raw data. We're not sending images, we're not sending movies or any raw user input. We send the difference in the model that we had versus the model that we obtained after retraining. So those are coefficients. Those are delta values of an old model and a new model. And those values cannot be traced back to raw user data. So we preserve the privacy of the user, and we still allow the network on the server to be enhanced. There are different ways for doing the enhancements at the server, and that is probably enough material for a few sessions as well. But this is what distributed deep learning techniques will do. So they will somehow average the input from the different clients, which is not extremely straightforward. I mean, a naive approach might be straightforward and just take the average of the inputs provided by the clients, but maybe some clients can be trusted more than others. You don't want a malicious client to ruin the performance of your network because it's sending bad input. So it's not as simple as just averaging the values of the clients. So, but that's out of scope for this presentation. So, in summary, with federated learning, you can really combine two great benefits. You can have a model that's being retrained, and you preserve the privacy of the user. And with Java and DeepLearning4J, the same code that you use on the server can also be used on the client, which makes it much easier to work on both the client and the server. And it allows the same people that are working on the server to also control the client application instead of having two different languages or two different approaches for doing client code and server code. And you don't have to worry about the performance of Java on the client, for example, because native BLAS implementations can be used on mobile and embedded systems. So the implementation is really fast. Great benefit is that you have immediate response on the client. You do not have to go to a server in order to get results. And the asynchronous training on the clients, for example, when devices are idle, allows you to benefit the most from the computational power of the devices without disturbing the user that with poorly performant applications. So, in conclusion, federated learning allows for enhancement of the model. It can be of a centralized model, actually. And it allows for the preservation of the privacy of the end users, which is getting extremely important. And it leverages the compute power of the devices. Now, I do realize that a single cloud instance has more computing power than a single mobile device. But if your application is used by a huge amount of users, then the power of those devices combined is probably significant, and it can save you some cycles in your cloud instances. Now, in order for federated learning to work really well, you need algorithms that work on both servers as well as on devices. And thanks to the right ones run anywhere, Java is a perfect candidate to do this. With Java on mobile and embedded clients, leveraging the same code as you use in the Java on the server, you can do this. And then you need libraries to make this happen. And the library that we showed here was DeepLearning4J. So all the pieces of the puzzle are there. It's up to developers to combine it and to create great applications that leverage federated learning, Java on the client, and Java on the server. This concludes my presentation. We will add a link to a Java code sample. We actually have a working sample for a DeepLearning4J application on iOS and Android. It's on GitHub, github.com/gluonhq. /Gluon samples. It's called Deep Learning Linear Classifier, but we will put the link probably somewhere online. If you have questions, you can ask them in the chat and in the YouTube chat probably. And with this, I think we can conclude my presentation, and I'm open to questions, of course.
Hello, and I better mute the other channel. Thank you very much, Johan. And before we continue with questions, I just wanted to also thank Oracle for their support and several people that are helping with this user group and with the transmission of this, the live event. Let me see if I can see any questions. I have something that I wanted to ask, but it's not directly related to this presentation, but I know that you are also involved, or you have been involved in quantum computing. Is that correct?
Yes, that is correct indeed, and more specifically in Java APIs that allow you to use quantum computing algorithms. So basically, it's the same. You can use Java and create applications that are highly scientific and that are still cross-platform. So quantum computing is probably a few years away before it can be used in mainstream development. But I think it's great that Java developers or scientists can combine science and development. So yes, indeed, quantum computing is one of the things I'm working on.
Do you see quantum computing as something that can completely change machine learning and artificial intelligence, cause a revolution of sorts?
Yeah, well, one of the most interesting, but also, to be honest, pretty complex potential applications of quantum computing is in machine learning as well. With quantum computing, it becomes possible to tackle problems in a completely different way, and it can handle problems that typically would require exponential time. It can solve them in polynomial time. So extremely complex neural networks or optimization of neural networks, if we can somehow translate that problem into a problem space that's easier for quantum computers, then those networks can really become huge. And then we're not talking about just Moore's law that will make them better and better and better gradually. It will be, well, really a quantum leap if we can combine them in an efficient way.
We have a question, but before that, we still see your screen. Do you mind maybe showing yourself, and then maybe to read it more awesome. So thank you.
If I know how to do that, I'll do it immediately.
Oh, you just did it. We can see you.
Oh, whoops.
Oh, now we see a lot of you. And me. No, we see you. That's fine. So the question is, what if you need to normalize training data?
Yes. What if you need to normalize training data? It's a valid question. Again, here and it's one of the more difficult parts. At least that's how I see it, of deep learning. But it's the same on the server as on the client. So typically on the server, you need to normalize data before you can really use it. And that's what I very briefly said. We can do some pre-processing. But the pre-processing can be done on the client as well. And that can be, for example, that if we have an image that we convert to RGB and have all the values between 0 and 1. But it can be, of course, completely different things. What is important here, and that's why I said we can have a few sessions about distributed deep learning, where the model on the or the network on the server takes into account all the changes submitted by different clients, because different clients probably need different normalizations because of different context parameters. So the normalization of the additional training data is definitely something that well, depending on what particular problem that you're tackling, but that should be taken into account if you're averaging the data of the different clients on the server. And that's why it's much more complex than just taking the mathematical average of the coefficients sent by the different clients. But that is where there's lots of work for data scientists, for example.
I see websites, for example, where people have to vote for the winning entry, whatever it might be, and over time they give different users more or less karma, or something like a karma that shows how trustworthy they are based on how they are complying with others, or how long they've been there. Or in Amazon, some users that give reviews are considered more trustworthy than others. So I guess you might use algorithms along the lines with that.
Yeah, absolutely. Yeah. Now, karma is one thing, but it's even more complex, because sometimes you would have a user who is very trustworthy, but who has a bad device. For example, his camera doesn't work well with colors, and therefore his interpretation might be different than mainstream interpretation. So it's it is complex. So by no means I wanted to say that using Java on mobile and deep learning for J, all your problems are solved. At the contrary, you still need real data scientists to add the real value to the problem.
Somebody is asking to share business use cases which are successfully addressed with edge computing that you share today. Yeah,
right. One example is it's something that's getting increasingly used in events at a conference. For example, it's crowd counting. For example, you want to you have an event, like for example the DevOps conference, which runs in a number of cities. For example, in Antwerp, in Belgium, and there are let's say 8 rooms, and people will attend one of the rooms to watch their favorite session, and you don't know how many people are already in the room. And as an organizer, you want to know that. You also want to know how many people are entering the room, when are they leaving the room, and you want to get an idea. For example, if in this room after 20 minutes half of the audience went away, then that means something. Maybe the speaker wasn't good, and you want to know that. So what you can do, and actually what happened at the DevOps this year, is you can have cameras at the entrance and exits of the rooms, and there you can count how many people are going in and going out. Now that sounds fine, but how do you count those people? Well, you do that by applying algorithms to the video stream, and you can detect people walking in and walking out. But typically, you don't provide a cloud on every camera. So what you might do in the first scenario is that you send all the video data from the cameras in the rooms to a server, and there you process them. But it's this video data contains videos of the users and of the attendees of the conference, and that means that you have to ask them permission, because the data is leaving the device. It's being sent to the cloud server. Now, if you have this on a Raspberry Pi, for example, with a camera attached, and if you have enough computing power on that Raspberry Pi to compute, to analyze, this is a user entering, another one entering, this is one going out of the room, this is 2 users going in the room, then you don't have to store or share the video, and you don't have to ask permissions from the user, because you're not storing the information and you're not sharing the information. So you use the power of the edge devices to make the predictions, and then you send, of course, to the server, you send 5 users entered at that moment and 1 user left at a bit later, and so the raw data is something that's not really valuable to the server, but the computed results, which is 1 user left now, 2 users joined, then that is something that is very relevant to the server. And it would be, you would lose lots of users if you ask them individually for permission. Can I use your image to see if you entered or left Rome? But if you're not using the raw data on the server, you can still use all the information because it's directly processed on the embedded device.
Okay, I don't see any more questions. So this is your last chance while we're still alive to write a question. So we're going to wait a few more seconds to see if another question pops up. And I see a thank you from the person who asked the last question. I'm afraid I will not say the name correctly. It's maybe Haider. But I don't see any new questions. I think that was a great presentation. I enjoyed it thoroughly. I'll put myself back on the screen. So thank you very much, Johan. Thank you for everybody who joined. And this presentation will remain on YouTube to be watched by everyone who couldn't make it to the live meetup. Thank you very much, and we will see you next year. And I'm going to end the presentation here. Goodbye.